Bersama Ziad, Hafiz, Daniel dan Roshan akan menerangkan tentang trigonometri. Jadi bahagian saya akan menerangkan pengenalan tentang trigonometri. Jadi untuk fungsi sinusoidal adalah untuk menyediakan anggaran yang baik untuk menerangkan kelakuan input dan output data. Dan ianya bukan sahaja dalam kejuruteraan elektrik, dan ianya juga diaplikasikan juga dalam cabang-cabang sains.
Okey, seterusnya adalah peralihan fasa dalam sinusoidal. Pertama adalah pergerakan fasai. Isyarat yang di luar fasa telah dianjak ke kiri atau ke kanan jika dibandingkan dengan isyarat rujukan.
Okey, untuk kembangkan fungsi sinusoidal dan cari perkara Fourier, jenis kembangan fungsi saja. Sinusoid arm VT melibatkan kosinus bagi perbezaan sudut. Dalam banyak aplikasi, anda boleh mengembangkan sinusoid arm menggunakan identiti trigonometri berikut. Mengembangkan sinusoid arm VT membawa kepada cos alpha tolak beta sama dengan cos alpha beta tambah sin alpha beta.
Today, I will give some introduction on complex number. Complex number have practical application in many fields, including biology, chemistry, economics, electrical engineering, and statistics. Most of our mathematical life we have been studying real numbers. Real numbers include things like 0, 1, and 0.3. These are the kind of number that we are familiar with. Then we explore something interesting. We explore the notion on what if there was a number that if we square it, we got negative 1. We define that thing as j, and we have a whole new class of number which you could really see as multiple of the imaginary unit. So the imaginary unit numbers would be j, negative j, and pi times j. So what if I combine imaginary number and real numbers? This is when a complex numbers was formed, where a and b are real numbers and j is the imaginary unit, where j square equal to negative 1. The number a is the real part of z and b is the imaginary part of z. Complex number also can be represented geometrically similar to a point in Cartesian coordinate system, with real numbers on horizontal axis and imaginary number on vertical axis.
Our video today we are going to actually explain complex number to create in the engineering stuff. We are about to actually use Euler's formula. So complex number is used to solve AC alternating current circuit. We also can use Euler's formula to solve this analysis to determine the independence of the circuit and the current flowing through the circuit. Other than that, as you can see on the circuit diagram, there's R, XL, XC, and AC. Those are state as resistor, which is R, over 25 ohms. XL is actually an inductive resistance, which is represented as G72 ohms, and also capacitive resistance, which is represented as G60 ohms, and also alternative current we conduct with 320 volts and 0 degree. Next slide please. So we can also relate it with complex numbers, which we know we can find a complex number by using a graph. So from here we can sketch a graph in the x-axis, which is going to represent as real number, and y-axis as an imaginary number. So from here we can get an equation such as 72 ohms minus 60 ohm, 60 ohm j. So we can know where our complex number are at in the graph.
To find the impedance, we use Pythagoras theorem to determine the impedance. So square root of 12 square plus imaginary 45 square, we get the answer is 46.57 ohm. So after that, we find the angle by using the formula inverse tan B per A, which is the B1 is 12 over A is 45. So we get the answer is for 15 degrees. So the final answer is impedance equal to 46.57 ohm, angle 15 degree. when we apply Polar form, we get 46.57 ohm. In bracket, cos 15 degrees plus imaginary sin 15 degrees. So now we can get the current by applying the Ohm's law, which is I over V per impedance. So the current, or I, is equal to 120 angle 0 degrees over 46.57 angle 15 degrees. 120 we must divide it to 46.57, and we get the final answer is 2.58. And then the angle we must subtract with each other. So 0 plus minus 15 degrees. So we get negative 15 degrees. So the answer, final answer is current equal to 2.58 angle negative 15 degrees ampere.
The next question that I'll be presenting is also the same AC circuit, but in these circumstances, the inductance and capacitance are given in the unit of Henry and also Farad. So, according to the principle of instrumentation and measurement that we studied in another subject, the inductance reactance is equal to 2 pi Farad multiplied by the inductance to find the inductance reactance. So we've got 2 pi multiplied by 50 hertz. The frequency is given on the diagram, 50 hertz times by 33 Henry. So we've got 10.37 ohms. That will be the inductance reactance, and the capacitance reaction, that will be easy as well. 1 over 2 pi Farad multiplied by the frequency multiplied by the capacitance value. So we've got 17.68 ohms. All right, what's the purpose of finding the inductance reaction? It's to apply the value into the equation that we're going to derive. So as we know from the Euler's formula, we know that Z equals to real plus real, which is the constant value, plus imaginary B. B is the constant value that's given. So we substitute everything. R, the resistor value, plus imaginary JXL minus JXC. Okay, we know that we cannot have the real part mixed up together with the imaginary part, but there's two J terms over here, so we can do simple arithmetic operation. So we just subtract it and we get this rectangular form that equals to 10 minus J 7.31 ohm. All right, and now we're going to convert the rectangular form into the polar form. So we've got to have this Cartesian plane, and we need to draw. So we know that this is 10, the real part, and the imaginary part is negative J 7.31, according to the equation that we just derived previously. So the Z, there is hypotenuse, represent the impedance. So as a very simple trigonometry, tangent theta equals to negative 7.31 over 10, then we can find the theta. All right, then after we find the theta, then we need to find the magnitude of the impedance using the Pythagoras theorem, 10 square, square root of 10 square plus the imaginary part 7.31 square. Therefore, now we can finally derive it into the polar form. We've gotten Z equals to 12.39 with a degree of negative 36.17 ohm. Alright, now that we found the impedance in the form of polar form, we can finally substitute the value of impedance into the Ohm's law. So we know that Ohm's law is V equals to IR. So we derive I, we've got to find the current across the AC circuit equals to V over Z, the impedance. So it's 100, the degree of 0 degree volt given in the diagram, divided by the impedance. Alright, in polar form division, the magnitude is divided to each other, 100 divided by 12.39, while the degree are subtracted with each other. So we got 0 minus 36.17, we got a positive value. Therefore, we got the value of the current, we get 8.07, degree of 36.17 ampere in the form of polar form. Note that the Euler's formula can be represented in three forms: polar forms, rectangular form, and also exponential form. But in this case, we are going to emphasize on the two forms, which is the rectangular form and also the what was it just now that we used? Polar form. Correct. So that's all for the example for complex number application in electrical engineering.